So, hello, Marco.
Hello, hello. Very nice meeting you.
Yeah,
Can see you
nice
again.
meeting you. Yeah, nice having you on board again. So, this is actually the third year in a row that you have been in this course.
That's true. That's true. Yeah.
Yeah,
First year was an invited talk, and
yeah,
then last year it was longer lectures, and I'm really happy to be here this year as well.
yeah. And now you're sort of taking like a real lecturer role in the course. So, and the same applies for Anna, which was just recently when we went on here. So, I think that those that are listening in now, this is the second session this evening for you guys. So, just hold on, and you can pause and finish off later. Like it's no problem. But if you ask questions in the Discord channel, that is the best way to do it. I will monitor questions um, all the time. But Marco, maybe you want to introduce yourself with a quick couple of words.
Yeah, I even have a slide about myself.
Okay, so maybe we should show the slide then. So
Why not? So let me. There you go.
yeah,
So I'm a research scientist in an institution which is called ICTP, the International Center for Theoretical Physics, which is a UNESCO Category 1 institution based in Trieste, Italy, where I coordinate a lab, which is a unit which is called Science, Technology, and Innovation. I actually did my PhD at KTH in Stockholm. So part of my heart is in Sweden. And I have been working on IoT for long and very long, since it was called sensor networks ages ago. And over the years, I organized many training activities all over the place, especially in developing countries. I think I did that in more than 30 different developing countries all over the place. I am the focal point of the ITU Center of Excellence in IoT, Big Data and Statistics, which is a UN, funded center of excellence. And I'm a visiting professor at Kobe Institute of Computing in Japan. That's the reason why I have this poster in the back in Japanese.
yeah, we need to
And
see a bigger picture of that.
yeah,
So
yeah, yeah, sure. But it
yeah,
looks like
now
a
we can see it.
okay. it it has dates in Japanese which I cannot read, but it's still
Yeah.
very nice. Yeah, that's me.
Oh, yeah, that's you. So with that introduction, so very much welcome, Marco. And your part in this course is the connectivity. I know that you're working with like all the areas in IoT, but like with your background and your focus, I guess that the connectivity is like the warmest to your heart, or is
Yes,
that
yes,
correct? Yeah.
yes, absolutely. We run a lab here which is called Marconi Lab. So we're really, we love, radios and antennas and setting up very long links and looking at new technologies and the kind of, appropriate and sustainable technologies for sensor networks.
Yeah.
So today I will share a bit about different options in the connectivity, part of IoT. So I think you learned about the IoT concept already, and now we're like getting a bit deeper in the different options. And tomorrow we will cover LoRa and LoRaWAN, which is right now the most promising technology for IoT devices.
Yeah.
But still,
And there
there are
will
many options, as you will learn today.
Yeah, and yeah, so good that you mentioned the LoRaWAN because it's already been a topic of discussion in the Discord channel, and I know that people are already starting to explore. And yeah, it's really interesting. And as you said, I think that it's a lot of what is happening in IoT today. It's often like LoRaWAN, you that's mentioned all the time, and it's a promising technology. Absolutely.
Yeah, from my experience in telecommunications in general, you also have these kind of waves, right? So very often technologies that were like popular a couple of years ago, then they are not interesting anymore, and then they become interesting again. So there's a lot of people working on DTN, intolerant networks, right
Yeah.
now, and that again lost a bit of attention a couple of years ago, and now it's a hot topic again.
Yeah.
Okay, so
Okay.
with that said, we can get started, I think, right?
Yeah.
Okay, um, so when we're going to go through these different communication options, we will consider different parameters. So one is range, right? If you think about IoT applications, you know that, I mean, some of them have a very limited range, and you're interested about sending data from a device to your phone, which is nearby. Other cases, you want to connect a whole city, or you want to put your IoT devices on a ship in the middle of the ocean. So range is an important parameter when you select the communication options. Multi-hop capability is also something interesting. It used to be a very hot topic a couple of years ago when people had this idea that devices should send data from one device to the other to then reach the internet in some way. Battery consumption, you have heard already about IoT, where the devices are powered by battery. So you want to have communication, technologies that don't use much of your battery. Security, that is embedded in some of the protocols, and it has to be taken into account for other protocols. And then you have cost, of course, as we know that IoT is about scaling these devices in enormous numbers. Well, the device, the communication part of the device should be cheap, but also the service should be cheap. So there might be cases where the chip on the IoT device is cheap and inexpensive, but then the service might be expensive. Availability, can you find this on the market easily? Well, that is to be taken with a grain of salt, because nowadays buying electronics, as you know, is not that easy, but still, availability is important, and regulation is another important parameter.
Yeah, and just to add to that, the availability is that we have like experienced that in this actual course at this moment. So it's a good learning experience for everyone that the availability is actually a concern at this moment. So, but you say that all these parameters, I think this makes a good point, and I guess that you will come to that later on. But like, there are no single solution. Often there is like a wide range of different parameters that you need to like think of. So it's like, is LoRaWAN the best, or is Bluetooth the best, or Zigbee the best? Well, as you always say, it depends.
It depends. Yeah, in fact, yeah. So we'll go through these different technologies and kind of consider, how they place in terms of these different parameters. But before doing so, it has to be said that IoT is a very specific case in telecommunications, because as we know, these nodes can accept low throughput for most applications. So we're sending, small amount of data, right? Temperature, humidity, number of birds if you're, developing an, beehive application. So in general, we're talking about low throughput. Second one is that we normally accept delays. So we're not talking about, video like we're doing right now, or audio messages. But again, if you send the temperature with a small delay, then that's fine. That's not really that important. In most cases, of course, there's cases where you activate something and this device has to be activated quickly. But in general, you can do with, longer delays. And finally, you have long sleeping times. So IoT devices usually sleep most of the time, then they wake up, they do something, and then they go to sleep again. So that again is a bit peculiar. So if you think about other, communication protocols and technologies, that's not the case, right? If you're talking about the Wi-Fi that we're using on our laptops, well, we're not sleeping most of the time. When we use our laptop, we, expect our communication to be working. So keep in mind these three, special cases of IoT: low throughput, possible delays, and long sleeping times. And in red here, many applications, but not all the applications. So please, think about applications where, on the contrary, throughput is important, and you want to send, lots of data. So again, you should consider, different technologies there. There's some concepts that are important to know when you're talking about, communications, and I'm sure that you kind of know about them, but just as a reminder. So one is spectrum allocation. So if you're talking about the frequency that you can use, Some of them you can use for free, and some others you have to pay for. So this is frequency allocation in the US. I looked for the one for Sweden, but I could not find it. But I'm sure it's available in some format, in document. This is nice because you see it as a picture, and you see that has many colors. So again, frequencies that are nearby, some of them are available for free, some of them you have to pay for.
Yeah, and do you call them ISM bands or often?
Yes, it's in the next slide. So ISM bands are specific bands which are industrial, scientific, and medical, and those are frequencies that you can use for free. So you don't need a license for them. And specifically, you have these 433 megahertz, 868 megahertz. There's a mistake there. It's 868 to 900 megahertz, and 2.4 and 5 gigahertz. So those are the frequencies that you use for Wi-Fi, for example. But these three specific bands that I show here with an arrow are the ones that you can use for IoT and that people normally use for IoT.
Yeah.
So of course, ISM bands, you do have the advantage that they're free. You can use them without any license. Of course, disadvantage is that there's many people using them. So if you want to have a super reliable system, then you might look for something that, a spectrum that you have to pay for, because again, you will be the only one using that spectrum. I added that this information changes, or it's a function of space and time, because these frequencies are different in different countries, in different places, and also in time. So, for example, the 868 megahertz frequency band that we use for the LoRaWAN just got extended a couple of months ago, and now you can use 900 megahertz for IoT as well in Europe, which wasn't the case last year, for example.
I actually didn't know about that, Marco. So
yeah. So just to say that these things again changing in space and time.
Yeah.
Good. One other very quick slide, maybe we'll get a bit more into this tomorrow, is power in a wireless system, because most of the time when you consider these different options, the first thing that comes as a question from kind of IoT engineers is, how far can I go? I got this question just a couple of hours ago from a colleague. He says, okay, I want to install this LoRa gateway, and then I'm going to deploy a device. How far can I go? And that's something that you cannot answer easily, because there's different parameters. And
actually, I can vouch for that, because I always get the same question as well when we talk about LoRaWAN. And actually, one funny thing is that if you drive an electric car, what kind of question do you think that you get?
Yes, exactly. That's
how far can you go?
Yeah.
and the answer is, well, it depends.
It depends, exactly. Yeah. And so in wireless systems, you have this very nice graph that kind of wireless engineers have as a tattoo, because they use it all the time, every day. And it says that if you have a transmitter and a receiver, then you have a number of parameters. So the output power from the radio is 1. Then you have a cable connecting that radio to the antenna, and in that case you lose a bit of power in the cable. And then you have the antenna, and the antenna, by its shape, kind of concentrates the power in a certain direction. So in some way you gain a bit of power. And then you have the path loss. That depends only on physics. So there's not much you can do for the path loss. And it's, of course, it depends on the distance. So the longer the distance, the more power you lose in this path loss.
Or if it's a concrete wall.
Exactly. Yeah. And then on the receiving side, again, you have an antenna, which in a way gains a bit of power because of its size and shape. You have the cable, where again you lose a bit of power, and then you have the radio, the receiving antenna. And so if the receiving power is higher than what is called the sensitivity, then the communication is possible. And funnily enough, the same scheme works for your FM radio. If you're picking up the radio in your car, the same scheme can be used, right? You have an FM transmitter somewhere with an antenna. You have a certain distance, so you lose a bit of power. Then on your car, you have an antenna, a cable, and the radio. Exactly the same scheme. If you look at GSM, exactly the same. If you look at satellite, it's exactly the same. So this is to say that when people ask how far you can go, it really depends, because it depends on the antennas you're choosing, it depends on the cables, on the transmit power, on the receiving sensitivity. So you can kind of play with most of these parameters. You cannot play with the path loss that is, embedded in nature, in a way, in physics.
Yeah.
So that's,
Yeah, I got a question here, an interesting
yeah.
question. Is if the transmitting power is good enough, is there any advantage to increase the sending power even though the communication already works?
Not really. So it really depends on the margin. So in this path loss, you might have additional losses, like you might have rain for some frequencies. You might have a tree which gets wet when it rains, and so you get additional power. So if you want your link to be stable and reliable, then you want to have this margin as large as possible, in a way. And
Yeah.
so then, increasing that power helps.
But increasing the power also increases the power consumption. And
Yes. For IoT devices, yes. One additional comment is that in most systems, you have bidirectional transmissions. So you might have your device that sends data, and every now and then you might have an acknowledge coming from the receiving side to your node. So
yeah.
this means that this scheme has to be applied in the reverse order as well. So meaning that if you have a device which has a very strong transmit power but a very bad sensitivity, then it will not be able to receive the message back. So when you do this calculation, which you can then do in an automatic way with some tools and so on, you have to do it in one way and also the other way around as well.
So when you're constructing a system, then like if you have some kind of, like I'm thinking about LoRaWAN now, that often there is a sensor, like some kind of device that is usually sending data, and you have a gateway that receives the data, and that is often one-way communication. Not much is sent from the gateway back, and even if so, so then the receiver is really good at listening, and not vice versa.
Right. Exactly. Yeah. Yes. Yeah. Good. So this is one concept that, again, you have to keep in mind when we're going to go through these different technologies. And if you have this question of how far can I go, it really depends from many of these parameters. Okay, there's another concept which, again, is kind of interesting, which is this line of sight and Fresnel zone. So if you plan some long links, then you might say, okay, I can see the other side with my eyes, or with a binocular. So the link is feasible. Well, that's not always true, because radio waves occupy a certain volume around this kind of optical link. And this is called Fresnel zone. And actually, the higher the frequency, the smaller is this Fresnel zone. But the point is that this Fresnel zone has to be empty, or at least mostly empty. I would say like 80% empty. And that explains why you usually want to put antennas on top of mountains. Because as you're on a mountain, you have this Fresnel zone, which is empty, even if you connect a device which is on the ground. So again, getting back to LoRa and LoRaWAN, some people experience very short LoRaWAN links, and they say, I cannot go over a kilometer. And from my experience, you can go, hundreds of kilometers without any issue, because it really depends on this Fresnel zone. And so if you put a gateway on top of a mountain, then it's much easier to have these very long links using LoRa because of this Fresnel zone. Okay, good. So let's start with our technologies. And the ones that we're going to consider today are Bluetooth and BLE, Wi-Fi, cellular, satellite, and then LPWAN shortly, because we'll cover more about that tomorrow.
Yeah.
So let's start with Bluetooth. I think we all know Bluetooth. We use it very often. It's the one that we use on headphones and so on.
Yeah, I have one in my ear at this moment. So.
Yeah, same for me. Yeah. So Bluetooth uses 79 channels, which are 1 megahertz wide, so it's quite wide, and it uses frequency hopping to solve the interference issue. Because using this 2.4 gigahertz band, it has to live together with Wi-Fi, with many other transmitters that use the same band. So frequency hopping means that you're changing these channels all the time in a kind of random way, which is then coordinated with the other device. But the main point about Bluetooth is that what you should remember is that it uses the 2.4 gigahertz band, which means that you can use it without any license. In fact, when you buy the headphones or other devices, you don't need to pay for a license. You don't need to pay to use that frequency because it's on ISM band. It has an architecture where you have a master node, which can control up to 7 active slave nodes, and then a huge number of inactive nodes. And they form what is called a piconet, a really small network. In fact, again, that's something that you do on your computer when you have a new Bluetooth device. You're the master on your computer, and the device is the slave. But you can have more than one of these piconets, which then form a bigger network, which is called a scatternet, by using what are called bridging nodes, which are associated to one or more master. So to show that in a picture, which is maybe clear, you have like a piconet on the left, you have a master, number of slaves, then you have another piconet on the right, number of slaves, and the slaves don't see, slave B cannot connect to master A, but then you have this bridge node, which kind of connects different of these devices, so you can form a bigger network. To be honest, I have never seen a network, an IoT network that uses Bluetooth in this way, to form this scatternet, but still that's, a possibility. Something which is more interesting, I think, for us is BLE, so Bluetooth Low Energy, because again, it's, lower energy. And it's a subset of the Bluetooth 4.0 kind of standard. It offers a mesh possibility, so that's quite interesting. So it's one of the few cases that we see today where one device can, route traffic to another device. So this is what we're talking about in sensor networks. And again, you have 40 channels, 2 megahertz wide, frequency hopping. It's the same as Bluetooth. And as we know, it is used in smartphones because, again, being low energy, it is more convenient. What is kind of interesting based on BLE, which you might use or you might consider using, is beacons. I don't know, Frederick, if you have, worked with beacons.
Yeah, we have, and I'm not sure if any of the students bought that one. Let's see if I can show myself in the bigger picture. But actually PyCom has a beacon, a Bluetooth beacon. Now my camera is filtering out, but yeah, there are these small beacons, and obviously many people might have the Apple AirTag. I think that functions as a beacon. Yeah, you have it on.
Yeah. There's another very one, right? The Ruby. I don't know if you use that from.
Yeah, I have the Ruby here as well. Yeah,
I think.
Yeah, it's my office. I have more or less everything here. So
it's from Finland, right?
Yeah,
it's a Finnish company. Anyway, so the idea of the beacon, which I think is kind of interesting for IoT, is that don't need to register with this device. You don't need to do this setup as we normally do with Bluetooth. So the beacon sends data all the time, and you can pick data with one or more devices. So again, I think it's quite interesting. Again, as in the picture, we show, if you have a mobile phone, so you can pick up data from an IoT device, which is sending information, and then you can visualize it on your phone. So I think for many commercial applications, beacons are really the way to go.
Yeah.
And there's like 2 standards. There's eBeacon with Apple, proprietary, of course, and the Eddystone from Google, which is open source. And then you have this Bluetooth. I don't know if it is active anymore, but it used to be kind of big. And if people have the PyCom device, there's examples for PyCom to send beacon messages.
Yeah.
So again, if we look at all the communication options, this is the easiest one. If you want to get started sending data from your IoT device to a phone, the easiest one is to go with a beacon. So again, range of Bluetooth is very limited because we're looking at kind of personal area networks. Multi-hop capabilities, mostly not, but yes, if you have this BLE. Battery consumption is low. We know that from our Bluetooth devices. Usually the battery lasts very long. There is security. Cost of the device is low. Cost of the service is free. There is no license. Good availability and good regulation. Again, it's ISM band, so we can use it for free. So second one, GSM. When I showed a picture with GSM, I need to download the latest figures because they change so quickly and the numbers are, staggering, of course. So we know that GSM is available almost everywhere. Again, this is especially true for industrialized countries. And if you move to developing countries, that is not completely true, but still penetration is huge. It's 5 billion subscribers, 4 billion internet subscribers, incredible number of SIMs, so 8 billion SIM cards. The other day I read the statistics saying that there's more phones than toothbrushes in the world. So we all know that this is unbelievable. 58% of 4G penetration, and there is even 5G, which is picking up. So you can use the same kind of GSM infrastructure for IoT with a technology which is called narrowband IoT. So you will learn tomorrow how LoRa works, but narrowband IoT works by making this channel super narrow. And in telecommunications, if the channel is narrow, then you can go long distance. And so if you look at the numbers here, you see that it's really in kilohertz, and the data rate is also very limited. So it is kind of really designed for IoT, where you want to send a small amount of data, but you want to go long distance.
Yeah.
So this is narrowband IoT. The advantage, huge advantage, is that you use the same infrastructure as GSM.
Yeah.
So these operators, they need to kind of update their software, change a bit the code in their base station, and then they can offer narrowband IoT connectivity.
Yeah, and I think that a large portion of the students in this course now have the FiPi, and all of them should have gotten a SIM card as well. So they should be able to use not NB IoT. I think I need to check that up. I think it's LTE Cat 1 because it's in Sweden. I think that's the operator.
Yeah.
I'm not sure about this, but I think
so. Yeah. So I had that in a slide where it says that if you have the FiPi device and you can add a SIM card, you can have a narrowband IoT on the FiPi. So that's really convenient. And I learned that that Telia was the first one in Sweden with nationwide narrowband IoT in 2018. So that should really be available all over the country.
Yeah, we are actually using that for one of the projects with the Beehive. Then we're using NB IoT with Telia.
So then if you look at the promise, I mean, what they're looking at is that high density. So tens of thousands of devices per cell. So one single cell can have, tens of thousands of devices. Data rate, as we said, is very, very limited. Low frequency of connections, again, meaning that you can send data, but not that often. And the modules, the vision was that it would be less than $5 for a battery life of more than 10 years. So again, this is kind of the vision and the promise, but it is really quite interesting. And getting back to the figure about the power that we showed at the beginning, it says 20 dB more compared to GPRS. So 20 dB is a lot, right? It means that the signal can be really, really, hundreds of times lower than what you got with GPRS, meaning that the coverage is really, really huge. In fact, I was looking, but I couldn't find the information. I think there was a link, maybe 1 or 2 years ago about a Swedish test, I think from Ericsson, which set up a super long link using narrowband IoT. and I would believe it was like hundreds of kilometers. So it can really go very long distance. Of course, disadvantage is that you depend on an operator, right? So I say the range is infinite because it really depends on the infrastructure that you have. So there is no multi-hop capabilities. Battery consumption usually is like medium when you use the GSM. I don't know, Frederick, your experience in that, but
Yeah, I would say that we have a mixed experience. We have been doing some tests. We are not really satisfied, but we are not sure if this is a firmware thing or yeah. But the battery consumption, in my understanding, should be quite comparable. Not as low as LoRaWAN, but not far from it. So
yeah. So maybe I should add medium or low. Yeah. Compare. Yeah. Security is there. I would say yes. Cost of the device is medium, I would say, maybe not as low as LoRaWAN. But again, the cost of the service, you have to pay for a service, right? So you're not independent and you're relying on one operator, which again, especially in the IoT world, is a bit tricky, right? Because if you have, you set up a network with, thousands of devices and the cost is low. And then if the operator decides that the cost will be higher, what can you do? You're locked, right? There's not much you can do in that terms. And then again, you depend on this infrastructure, which is available but still limited. If you're talking about ships, for example, in the ocean, then that wouldn't be feasible. You need to look for something else.
And I got a comment here that what do you mean by infinite range? And I think we just need to clarify that it's not infinite range of the radio that you mean.
It's infinite range, meaning that really it depends on how large and extensive is your GSM network. So yes, you're right. It's not infinite range in terms of one link, but if you install other base stations, then you can reach more places.
Yeah.
I don't know about Sweden. I mean, is all the country covered, even kind of remote areas by GSM?
I think more or less yes, but I actually this is a killgissning in Swedish. I'm actually not sure. I think the northern parts of Sweden and in the countryside there might be spots when there is not much coverage.
Yeah.
So.
Okay, excellent. So this is GSM. Then let's move to Wi-Fi. Well, we all use the Wi-Fi. Again, I looked for this latest information from the Wi-Fi Alliance, and they said in 2022, or just now, 18 billion Wi-Fi devices will be in use. So, I mean, unbelievable number, huge success, and not just success, but it's a success of an ISM band, right? So you have this small chunk of frequencies around 2.4 megahertz and 2.4 gigahertz and 5 gigahertz, which were given for free. And now this is the most valuable and the most popular ways of communicating, right? You have Wi-Fi all over the place, on planes, as we know, and in all sorts of devices. So incredible success. And so the point is, can you use this for IoT communications? And we have to go a bit back about different protocols in Wi-Fi that we often see as one single protocol. We use Wi-Fi, but it's actually quite diverse. So it started with A and B in the old days in '99, very limited data rate and different frequencies. A was using 5 gigahertz, B was using 2.4 gigahertz. Channel was a bit limited, but now if you move to the newest one, let's say AC, for example, that we have on most access points nowadays, you get 3.2 gigabits per second, huge throughput. On 5 gigahertz, very wide channels. They have very advanced technology in MIMO and different antennas. As you know, if you buy an access point now, you have 8 antennas on that access point.
Yeah.
But the point is that people then have thought about extending that to use IoT devices as well. So in 2016, they applied for this AH family of protocols, which uses one sub-gigahertz band. So the lower the frequency, the more you can penetrate into buildings, into vegetations, and in some way you go, longer distance. So most commonly around 900 megahertz. Again, it's a low power protocol, longer range, kind of Wi-Fi, and they say up to 1 kilometer range, but actually can go longer. And it has low power consumption because you have this sleeping mode. And the channels are wide, but not as wide as the traditional Wi-Fi. And in their vision, it competes with Bluetooth with limited speed. So I looked for devices because actually I have never used it myself. I don't know about you, Frederick, but
No, I haven't. No.
it's not that popular. But there are some commercial devices. This Silex technology produces some devices on the market, so stuff that you can buy, and you can connect to see more than 600 devices. So Wi-Fi again has these kind of two different options. So you can use the traditional device, Wi-Fi, which we have in every house, in every university. So if you're planning for an IoT application that has to do with homes, with domotics, it's actually a really good idea to use Wi-Fi because most people have it at home. So the range, I would say 1 kilometer, but this is not really true. You can go very long distance. We set up in our lab the world record of the longest Wi-Fi was 400 kilometers using really big antennas and off-the-shelf equipment. But let's say normally it's about 1 kilometer. There is no multi-hop in Wi-Fi, as you know. The battery consumption is average. So you know that when you use your laptop, it consumes quite a lot of power if you use Wi-Fi. You do have security. Cost of the device is really low. So these Wi-Fi chips you can buy for nothing. In fact, I would say all the IoT devices that you have, even the cheapest one, you always have Wi-Fi option.
Yeah.
And cost of service is free. You use ISM, so it's really well regulated and it's really widely available. Did you work on any project with Wi-Fi, Frederick?
I think that more or less, like we have, but I would say that more or less every project, like when the students are working on something, they start with Wi-Fi. I mean, that's most convenient. So even if you're exploring other options, it's so easy to start with Wi-Fi. But then there are also, I mean, you have this ESP now that actually is built in, uses Wi-Fi, but not an access point. So you can also use Wi-Fi for direct communication between two devices.
That's a very, very, very good point. So this opens, the issue of how do you set up these devices? Because again, if you're talking about a small project, then okay, you have a PC, you connect your device on the PC. But let's say that you want to install, a weather station, or you want to connect, different sorts of devices. So now in many of these commercially available devices, they do have Wi-Fi and they act as access points. So I just used a weather station the other day, and when you buy it, it acts as an access point. You connect with your laptop and you get a web page. On that web page, you set up the LoRa aspects. And then when you're done, the device, uses that setup and the Wi-Fi is not available anymore. Yeah. So it's also a very good way to connect to device for setup.
Yeah, and maybe, I mean, when like people might ask that, oh, I don't get that 1 kilometer range of my Wi-Fi at home. But as you say, it depends. So, but like the normal scenario for a Wi-Fi network is that when you have a consumer Wi-Fi router, well, it might be 20 meters as well if you're counting walls and put the Wi-Fi router in a bad place. So
yeah. Again, if you put it on the top of a mountain, you will get a much longer range, even with off-the-shelf equipment. Yeah. Okay, super. The next one is kind of an interesting one because it's satellite. So you might think that satellite. Why should I use satellite for IoT? But then, if you think about the number of applications where these devices are in really remote places, well, satellite is an option, and it used to be an expensive option up to a couple of years ago. Now, I think it's something that you should really consider because it's not that expensive anymore. I give a few examples here. This is an Iridium-based chip So Iridium is really popular. They have a very good coverage all over the place. In the middle of the jungle, you still have, coverage from Iridium. And I just put here some information about the chip, just to show that the issue here is not the chip itself, which is small and, quite inexpensive, but it's the transmit power. So you can see some values here where it says that transmit power peak is 1.3 amperes. That is a huge amount. And even the average one is 145 milliamps. So I'm sure that you will go through this math, later in the course, but it tells you that the battery will be depleted quite quickly. And then if you look at the cost, well, that in an kind of surprising way, the cost is not that much. This is just one operator, and you see that, sending like one credit, which is like sort of an SMS kind of message where you can send some, temperature, humidity, pressure, some GPS information is, tenth of an euro or something, tenth of a dollar or something. But my point here is that it's affordable, so it's not that expensive. And
I can show you. I mean, I'm just changing the slide there, but yeah, we have this. This we actually have in the lab now. Maybe that is your next slide. So
it is. It is. It is. So just to say that there's even more. I mean, even cheaper solution. So Iridium, I showed you Iridium because the coverage is, excellent, and you have the satellite all the time. So if you need to have some real-time data send, then you might, consider Iridium. But if you're happy with sending data on a regular basis, I will show you in a second how often. There is this swarm.space. Frederick just showed the website. That is a new technology. It's based on this low Earth orbit satellite. And you can see the figures here about the price. So it's $90 for the chip, which again is quite inexpensive. So you might, get that for your project, and then you're able to send data from the middle of nowhere. They have this evaluation kit, which Frederick has. I'm, jealous because you have it and I cannot use it here in Italy because of regulation. So they have some commercial deals with some countries. So for example, in Sweden, you can use it. In Germany, you can use it. In Denmark, you can use it. In Italy, you cannot use it. So the technology is there. Technically, I could use it in my place, no issue, but I cannot do it legally. So you have all these regulations from satellite. And again, the data plan, you see, it's $5 a month per device. And you can send these 750 data packets per device per month. So quite inexpensive. You can, again, think that you're in the middle of nowhere on a ship or in the jungle, and you can send data from the device with $5 per month. I did this. You can on the Swarm website put a site. I put Kalmar, and it shows you that you can get a pass from the satellite. I would say roughly every hour or so. So again, it's not real time. You need to wait for the satellite to pass on top of your place. But I think once every hour is more than okay for IoT data. Again, if you're thinking about weather stations or most applications, one pass per hour is perfectly okay.
Yeah.
So another solution is another company in the UK called Lacuna Space, which actually was the first one to offer satellite solution based on LoRa. And again, the application is tracking assets, for example. And they do have these devices produced with Semtech, which is the company that produces the LoRa chip. And you see it's really small. It has a very nice design for the end node. So this device is small. You might remember the old days when satellite, you had to require a satellite dish to communicate with the satellite. And nowadays these devices are really small. But to be honest, they're still not available on the market. So you can test them for short time. You can ask them as universities to get one of these devices, but you cannot buy them. So I think Swarm is a bit more advanced in that point of view. It's a picture of us testing this Lacuna space in Uganda just before the COVID outbreak. So we were waiting for the satellite to pass on top of us. So the way these devices work, both the Lacuna and the Swarm, is that they have a GPS on board. So they know where you are and they calculate when the satellite is going to pass on top. So they're in sleeping mode most of the time, and then they know that the satellite is passing, so the data is sent. So they're kind of well designed and quite clever, and they optimize power consumption in that way. So again, range, again, infinite.
Yeah.
Take it with grain of salt, because it really depends on the coverage that you get from satellite. No multi-hop. Battery consumption is usually quite high, I would say, or medium high. I mean, if you talk about, I don't know your experience, Frederick, with the Swarm. I don't have
We haven't
it.
measured the power consumption, to be honest, so I don't know.
But
I really
yeah,
can't say.
yeah. But usually, again, you need to send data up there, so it's a bit high.
Yeah.
I would say security, I would say no, but it really depends, right? But you're relying on a company that is picking up your data and encrypting your data. So you need to take care of the encryption yourself if you want your data to be perfectly secure. But the issue here is the regulation. So again, Swarm, I cannot buy from Italy. You can buy it in Sweden. If you move to other countries, the regulation is even more complicated. So satellite does require, an authorization, even as a user in some way. Good. So if there's no question up to now, we just
No, actually
okay.
not. So yeah.
So just few slides about LPWAN to set up the scene for tomorrow. And LPWAN stands for Low Power Wide Area Network. So the idea since the beginning was, can we set up a technology that can cover a wide area? It all started with these smart meters, and the idea was, can we put one gateway in Kalmar and cover the whole city with that gateway, so that all smart meters will communicate with that gateway, and then it's easier to set up these IoT networks. So it doesn't really work that way, but the point is that you want to cover a wide area. And those are technologies that are designed for low power. In fact, they're designed specifically for IoT, where usually you go with low data throughput, which means that you have higher sensitivity, which means that you have a long range. So the three concepts are like linked together.
Yeah.
And then you want to do it low cost, both in licensed and unlicensed spectrum.
Yeah. So I think that you make a good point when we go into the LP1 here, that this technology is sort of made for IoT, so sending small amounts of data. But GSM, Wi-Fi, well, they're not made for IoT. They're really good for it depending on what you're aiming to do. But yeah.
Yeah. So in fact, if you start looking at the characteristics, so let's say that you have range on one axis, and then you have data rate on the other one. Well, we said that, for example, Wi-Fi, you have a limited range, but you have a high data rate. So it's there on the top left, right? Then we said, Bluetooth, well, the range is very limited, up, a person, couple of meters, but the data rate is also limited. So you cannot send, video using Bluetooth. On the top right, you have protocols where you have long range and high data rate. So for example, again, narrowband IoT. And then on the bottom right, you have long range and small data rate, which is what we're interested in. So we have IoT devices, they send small amount of data, but we want that to be long range. Then if we add another graph here, which shows power consumption and data rate, then we need to shuffle things a bit, because we have on the left, bottom left, we have all these protocols that have a low power consumption and a low data rate. So again, we have LoRa and Sigfox, low power consumption, low data rate. But then top right is Wi-Fi. We said Wi-Fi consumes a lot of power, so it's in the top right, and it has a high data rate. Bluetooth is like, I would say, in the middle, right? So power consumption is so and so, Then you have Bluetooth Low Energy, which is better, but traditional Bluetooth, you might remember, uses quite a lot of power. And it has like an average data rate. But we're interested in the ones which are in the corner here, which have, low power consumption and low data rate. So if we add the two graphs together, we mix them, we understand what is this LPWAN. So LPWAN is about having long range and low power consumption. So there we have like these four protocols in a way. We have narrowband IoT, we have LTE, we have Sigfox, and we have LoRa. So all the others don't really fit that niche of having long range and low power consumption. Because again, as Frederick just said, I mean, if you're talking about Wi-Fi, well, you might use it for, projects. It's, if you use it at home, it's fine, but it's not really designed for IoT because the range is limited, the power consumption is high. Of course, availability is also very wide. So you have many, access points with Wi-Fi compared to the number of access points you have with LoRa. And then if you look at GSM, again, range is large, but power consumption is huge. So tomorrow we will dig a bit deeper into this, bottom right side of things. We have longer range and low power consumption.
I got the question here about the
Yes.
Starlink. So I've actually answered a little bit but when we talk about the Starlink, that is, well, as I explained in the Discord channel here already, that, well, you have a high data throughput, so it's really good for broadband. But I think that Starlink consumes about 100 watts. So driving that on battery it wouldn't be a feasible option. Well, you need a large battery then, but
yeah. By the way, this company Swarm has been bought, right, by the same company that is running Starlink. So
okay.
in some way, they're part of the same company. And it all falls into this new kind of era of this LEO satellites, right? So low Earth orbit satellite, where there's a huge amount of satellites because it's really cheap to send them up, dozens of them or even hundreds of them. It's really inexpensive. So that opens some issues. I mean, kind of ethical issues in a way, where we're sending lots of satellites up there, and if something catastrophic happens, I don't know who is going to solve that issue. There is a regulation issue, so it's a bit of a Wild West right now in terms of this LEO satellite. But on the kind of positive side is that we're going to get more and more satellites that can get data from our IoT devices. Yeah. So yes, Starlink is the same technology in a way, this lower orbit, but it's, as you said, much more power hungry than this Swarm.
Yeah, and I think that, I mean, if you are interested in this Swarm satellites, if you go in and read about like how the satellites are, how big, how small they actually are. We're talking about 10 centimeters squared, like 10 centimeters and about 2 centimeters thick. So they're like tiny satellites, really
it's
tiny.
It's like a sandwich, right?
Yeah.
In a way. Yeah, it's unbelievable.
Yeah, it really is. So it doesn't seem that we have that many questions, and we are already a couple of minutes. No, we're not over time. We started a little bit late, so yeah, we are actually on time. But tomorrow we'll go into LoRaWAN a bit more specifically, and actually got a question about antenna and LoRaWAN, but I think I'll keep that question until tomorrow. It will make more sense when we talk about LoRaWAN tomorrow.
Excellent.
Yeah.
Perfect. So see you tomorrow then. We're going to see why this LoRaWAN is so exciting and why we're all excited about LoRaWAN.
Yeah, we always need a cliffhanger. So hang on, and we'll see you tomorrow. Okay, thank you very much, Marco.
Thank you very much for the invitation.